second one. So for the first of our starter problems here, x to the third plus 3x minus 2x minus 2 is less than or equal to 4. First step, of course, is always to set it comparable to 0. So I subtract 4 from both sides. So this is x to the third plus 3x squared minus 2x minus 6 is less than or equal to 0. Now that we have it compared to 0, it's time to try to factor. This is more than 3 terms, so I'm going to try to group it, making sure that negative goes with the 2x. X squared factors out of this first one, leaving me with x plus 3. This next one, actually a negative 2 will factor out, leaving me with x plus 3. So now we've got the x squared minus 2 times x plus 3 is less than 0. So we solve each of these pieces. Now this one here being x squared minus 2, of course, we're going to solve it as equals 0 for now. Equals 0, as I solve that, I would add 2, and so x squared equals 2, and then I would square root to get that x equals the positive or negative square root of 2. So there's 2 of our critical points on our number line. The other one here, x plus 3 equals 0, I solve that by simply subtracting 3 to get x equals negative 3. So those are my 3 critical points on the number line. Any questions as to where I got those 3 so far? So on my number line, I'm going to put those points on there. The square root of 2 is about 1.414. So negative square root of 2 is somewhere in there. Positive square root of 2 is somewhere in there. Then I had x equals negative 3 would be right there. So I have 4 different regions to test. So I'm going to test this region over here by using the point negative 4. So my equation, x to the third 3x right there. I'm going to test in negative 4. So negative 4 cubed plus 3 times negative 4 squared minus 2 times negative 4 minus 2. Is that less than or equal to 4? Negative 4 cubed is a negative 64. Negative 4 squared is 16 times 3 is 48. Negative 2 times negative 4 is a positive 8 minus 2. Well, this adds up to negative 10, I believe, which is less than or equal to negative 4, or less than or equal to 4. So that's telling me this region here is true. So I'm going to test this next region by using x equals negative 2. So negative 2 to the third plus 3 times negative 2 squared minus 2 times negative 2 minus 2. Is that less than or equal to 4? Negative 2 to the third is negative 8. Negative 2 squared is 4 times 3 is 12. Negative 2 times negative 2 is 4, and then minus 2. Well, negative 2 plus 12, or negative 8 plus 12 is 4, plus 4 is 8, minus 2 is 6. That is not less than or equal to 4. So that region is not a solution. So the next region, I'm going to take 0 just because that's always an easy point to test. So we got 0 to the third plus 3 times 0 squared minus 2 times 0 minus 2, which leaves us with simply negative 2. Everything else zeroes out. And negative 2 is definitely less than or equal to 4. So that region is true. And now we're assuming this region over here is probably false, but we're going to test it just to be sure. Test x equals 2. Two to the third plus 3 times 2 squared minus 2 times 2 minus 2. Is that less than or equal to 4? 2 to the third is 8. 2 squared is 4, plus times 3 is 12. Negative 2 times 2 is minus 4. 8 plus 12 is 20, minus 4 is 16, minus 2 is 14. That is not less than or equal to 4. So it confirms that region is not a solution. So our solutions here in interval notation are negative infinity up to negative 3. It's less than or equal to, so it's a square bracket. Unioned with negative square root of 2 to positive square root of 2. Again, less than or equal to, so those are both square brackets. That's our solution. How many of you had that? Show of hands. Questions on how many of you would have had that if I'd given you more time? Okay, perfect. I'll give you a couple more minutes then to work on the second problem here. I'll give you about 4 or 5 more minutes to work on that one. Let's see how you're doing on this one so far. So when we're dealing with these rational inequalities, just like with the polynomial inequalities, in the polynomial inequalities here, all we cared about were the zeros or the roots. Over here, we care about the roots, but we also have to worry about vertical asymptotes. So to find the roots, what we're going to do is we're going to use the numerator we're going to set it equal to 0. 3x plus 5 equals 0. Subtract 5 to get 3x equals negative 5. And finally, we'll divide by 3. X equals negative 5/3 is a root. So the numerator gives us the roots. The vertical asymptotes come from the denominator. And we find them by setting the denominator equal to 0. 6 minus 2x equals 0. We subtract 6. Negative 2x equals negative 6. And we divide by negative 2 to get that x equals 3 is a vertical asymptote. So what that's telling us is on our x-axis here, we have critical values at negative 3 and at negative, oops, get my marker to change here. Sorry, not negative 3, sorry, positive 3. And at negative 5/3. So we have three regions to test here. I am going to test down here by using -2. I'll test this one as 0, and they'll test this one using a +4. So let's start out with that -2 first. So if we test x equals -2, we have 3x plus 5, 3 times -2 plus 5, over 6 minus 3 times -2. Making sure I got that right. What's that? Two times, thank you. So we go ahead and work this out on top. Again, I'm going to take some shortcuts. 3 times -2 is -6, plus 5 is -1. -2 times -2 is a +4. 6 plus 4 is 10. So this is a -1/10. I forgot to put in the inequality here. It's greater than 0. This -1/10 is not greater than 0, so that's not true. So that region is not a solution. So in our next region here, let's test 0. So 3 times 0 plus 5 over 6 minus 2 times 0. Is that greater than 0? 3 times 0 is 0, plus 5 is 5. 2 times 0 is 0, so 6 minus that is 6. 5, 6 is definitely greater than 0. So that region is true. Let's test our last region over there using the 4. Since that x equals 3 was a asymptote, not a root. Generally at roots, if it's true on one side, it's false on the other. But with an asymptote, there's no way of knowing. So 3 times 3 plus 5 over, 3 times 4 I said, didn't I? Should be 4 I'm testing there, not 3. 3 times 4 over 6 minus 2 times 4. Well, 3 times 4 is 12, plus 5 is 17. -2 times 4 is -8. 6 plus -8 is a -2. 17 over -2 is not greater than 0, so it's not true over there. So our interval here, this was strictly greater than, so it's going to be open-ended. So round brackets, -5/3 to 3 is my interval. I realize there are a lot of steps in those, so be patient with them. It took us over 20 minutes just to do 2 of them here working together. So these are ones to be very patient on. Does anybody have any questions off the homework from last Wednesday that they want me to go over? Okay. So the other thing we covered last Wednesday was variation. And variation is just, the biggest part is getting the right form of the equation. If it states inverse variation, make sure you have y equals k over x. It says direct, make sure you use the form y equals k times x. Okay, well, today we're going to start a discussion of exponentials and logarithms. So far, we've looked at a lot of equations with exponents in them. Y or f of x equals something like 3x squared minus 5x plus 2. Things like that there's exponents in them. The x squared is an exponent, but this is not an exponential equation. This is a polynomial. In a polynomial equation or a polynomial function, the variables are part of the term, but the powers are whole numbers. 0, 1, 2, 3, 4. Even rational equations, y equals 2x over 3x squared minus 12. A rational function, there's powers in it, there's exponents in it, but the powers here are integers. When we're talking about exponential functions, we're not talking about either of those. When we talk about exponential functions, we're going the next step to where the power of the function is not an integer or a whole number. The power is the variable, usually x. So y equals 3 to the power of x, or f of x equals 3 to the power of x. That's an exponential function. An exponential function has a general form. F of x equals a, which is generally some starting amount, times some rational number, r, usually call it the ratio, to the power of x. If you look at this kind of function, a times r to the power of x, when x equals 0, what does r to the x have to equal? No matter what r is, if it's to the power of 0, it has to equal 1, right? If you recall, anything to the power of 0, 98 to the power of 0, it's 1. 254 to the power of 0, I get 1. Even if it's a negative number, negative 38 to the power of 0, I get 1. So anytime x equals 0, the value of that function is a. So let's go back to that first example. F of x equals 3 to the power of x. In that example, a equals not 3, but 1. Since it's just 3 to the power of x, you can think of that as f of x equals 1 times 3 to the power of x. 1 is that initial value that we're multiplying by. And then, of course, our value here is, sorry, the a value, little a, is x, or sorry, 3. It's 3 to the power of x. Let's graph this. Let's do a table and get some values for this and get a form for this. So if x is a negative 3, 3 to the power of negative 3, remember it's 1 over 3 to the power of 3, well 3 to the third is 27. That's 1 over 27. So if I'm going to graph this on my graph, gives me the ordered pair negative 3, 1/27. So that's like really close to 0. If x is negative 2, 3 to the power of negative 2 is 9, or 1/9. So at negative 2, it's 1/9. Still pretty close to 0. If x is negative 1, 3 to the power of negative 1 is 1/3. So at negative 1, we're at 1/3. If x is 0, 3 to the power of 0 is 1, like we just said. If we keep going, if x is 1, well, 3 to the power of 1 is just 3. The ordered pair 1, 3. If x is 2, 3 to the power of 2 is 9. Give us the point 2, 9. So you can see the shape here is a curve. Two properties of this curve. As we go off to negative infinity, it approaches 0. Now, it will never equal 0. Each time I move over one spot, it's going to get cut by a third. It's going to get closer and closer to 0, but it'll never equal 0, which means the x-axis here is a horizontal asymptote. On the other side, what happens? Of course, at 0, it equals 1, which you think of these as a change over time is what these functions, these exponential functions usually represent. At 0, at the beginning, things are equal to 1, or the whole thing. And that's what that represents, is one whole amount. As you go to the right, the value increases and shoots up to positive infinity very quickly. So as x goes to infinity, it approaches infinity. But there are other possibilities that can happen. Let's look at another fairly simple exponential. Y equals 1/2 to the power of x. I guess I put in y, so I put y in there. So as I plug in values for x here, if I use -3, 1/2 to the power of -3 is 1 over 1/2 to the power of +3. Well, 3, 1 over 1/2 to the +3. 1/2 to the +3 is 1/8. 1 over 1/8 is just 8. We try that on the calculator, 1/2 the power of -3, it does give us 8. So that gives us the ordered pair -3, 8, which is actually up off the top of our graph here right now. -2, we had the same type of thing. 1/2 to the power of -2 is 4. So at -2, we're at 4. At -1, 1/2 to the power of -1 is 1, is 2. So at -1, we're at 2. At 0, anything to the power of 0 is 1, so we're still at 1 there. At 1, well, 1/2 to the power of 1 is 1/2. So we have the ordered pair 1, 1/2. And at 2, 1/2 squared is 1/4. 3, I'm out of room in my table, but 1/2 to the third would be 1/8. So again, I get a curve that at 0 goes through the value of 1. As I go into one direction, in this case, as I go off to positive infinity, it approaches 0. And in the other direction, in this case, as I go to negative infinity, it approaches infinity. This curve, you'll notice, is exactly backwards to the one we had in our last example. So the big question is, what's different? Well, we have that general form of the equation, y equals big A times little a to the x, or little a to the t, whatever you want to do. If little a in the first example was 3, so it went in this direction, with that being 1. Well, if little a is bigger than 1, that's what happens. If little a is less than 1, and I should be careful, because it can't be negative, so if little a is between 0 and 1, that's when the curve goes the other way. There are special names for these. Little a being bigger than 1 is called growth. You see, it gets larger as it goes to the right. Little a being less than 1 is called decay. The value gets smaller as the values of x increase, decay. Now, these functions are very, very useful in a lot of ways. First thing we see with them is as we're analyzing the function, the domain. There's absolutely no value that is off limits for x here. And that y equals, or f of x equals, big A times little a to the x. The domain is negative infinity to positive infinity. The range in the standard functions we've looked at so far, it approaches 0 and then it shoots off to positive infinity. Notice it never equals 0, so we have that round bracket there, non-inclusive bracket. Now there are things we can do to alter the location of this function. Remember, when we had our other functions like y equals x squared, things we could do is we could add or subtract to the x. I'm just going to say adjust x. If I had y equals x minus 1 squared, remember, whatever happens in here, we move the opposite direction. That moved it to the right 1 unit. If it was plus, y equals x plus 1 squared, that moved it to the left 1 unit. To move it up and down, we had the same relationship with x, or with y, sorry. To adjust y, I had y minus 1 equals x squared. That minus 1 moved it the opposite direction, up 1. Typically, however, we didn't leave it written like that, because if we put it in f of x notation, we don't want anything on the left side of the equation with f of x. So we want to get y by itself. So we wrote it as y equals x squared plus 1. Sticking with that, if it was y equals x squared minus 1, that one shifts the graph down 1 unit. So with our exponentials, we have exactly the same relationship. Y equals 1/2 to the power of x. Should put that in parentheses. Looked like this. If I alter that, y equals 1/2 to the power of x minus 2. I've adjusted the x. Remember, I always go the opposite direction. So what direction is this graph going to move? To the right, 2 spots. So I'm going to go 1, 2 spots to the right. So my graph just slides over that 2 spots to the right. Y equals 1/2 to the power of x plus 1. What direction is that going to move? Up 1 spot. So this point just goes up 1 spot to there. Y equals 1/2 to the power of x plus 3. What's going to happen there? So you left 3 spots. Perfect. And of course, the only time it'll go below our x-axis is y equals 1/2 to the power of x minus 2. That means it's going to move down 2 spots. So you're down 2 spots. It's going to go through there. We'll notice one of the changes with this one is now the horizontal asymptote is no longer y equals 0. It's no longer the x-axis. The horizontal asymptote is now y equals -2. This one up here in green, I drew it poorly. We'll redraw that. Should look like that. The horizontal asymptote there is no longer the x-axis because we shifted up 1. That horizontal asymptote is now y equals +1. So the asymptotes shift with the rest of the graph. Well, we have, in all of our examples so far, we've let big A equal 1. Well, what if big A is not equal to 1? Well, if you recall from our other graphs, multiplying the x variable is a dilation. It stretches it out vertical or horizontal, or it can flip it over, opening up to opening down. So let's try f of x equals 3 times 2 to the power of x. So if we make a table here, of x and f of x, if x is negative 3, 2 to the power of negative 3 is a negative, or sorry, is positive 1/8. Times 3 is 3/8. So we got negative 3, 3/8 is that ordered pair. Negative 2, well, 2 to the power of negative 2 is 1/4. Times 3 is 3/4. So negative 2, 3/4. Negative 1, 2 to the power of negative 1 is 1/2. Times 3 is 3/2. So at negative 1, we're at 3/2. And if x equals 0, 2 to the 0 is 1, times 3 is 3. So you'll notice the first big change you see is instead of being at 0 for our y-intercept, we're at big A, in this case the 3. We keep going. If it's x is positive 1, 2 to the 1 is 2, times 3 is 6. So 1, 6. And then we're probably going to run out of room after this one. If x is 2, 2 to the power 2 is 4, times 3 is 12. So 212 is right there. So you can see what has happened with that value of big A here is it has dilated our graph. It's stretched it out vertically. Actually, I probably shouldn't put the arrow down because it really just stretches it out going up. We still have 0 as our horizontal asymptote, but instead of going through 1, we go through 3, and it goes up faster. It stretches it out. It's almost like increasing the slope. So what if big A is a smaller number? What if it's f of x equals 1/2? Well, let's make it a little more interesting. 1/3 times 2 to the power of x. So if x is negative 3, 2 to the negative 3 is still 1/8. 1/3 of that is 1/24. So it's really small there. Negative 2, 2 to the negative 2 is 1/4, times 1/3 is 1/12. Still pretty small. Negative 1, 2 to the negative 1 is 1/2, times negative, or times 1/3 is 1/6. Still very small. At 0, 2 to the 0 is 1, times 1/3 is 1/3. At 1, 2 to the 1 is 2, times 1/3 is 2/3. At 2, 2 squared is 4, times 1/3 is 4/3. 3, 2 to the 3rd is 8, times 1/3 is 8/3, or 2 2/3. So you can see this, of course, contracts it, or makes it increase a little more slowly. It's time for a break, but I'm going to put this up here for you. F of x equals negative 3 times 2 to the x. So when we get back from break, if you would like to start working that out, and we'll graph it and see what that looks like on our graph. Let's go ahead and take 10 minutes or so. It's a couple seconds here from 10:20. We'll come back at 10:30 and keep going. So for this problem here, it's actually very closely related to this one. F of x, f of x equals 3 times 2 to the x, and f of x equals negative 3 times 2 to the x, it just flips the graph over. So that's how I wanted. Do my color back here. So we end up getting a graph that looks something like that. So you could probably guess if I switched it around and did f of x equals negative 3 times 1/2 to the power of x, we have the opposite effect. Up here, sorry, it should be 1/3, I should say, to the power of. I will do this. Negative 3 times 1/2 to the power of x. 1/2 to the power of x, if you recall, went backwards like this, going through 1. 3 would have stretched that out vertically. 3 to the power of 3 times 1/2 to the power of x would have stretched it out vertically like this. Negative 3 flips it over and stretches it out. So just like multiplying that number by a parabola stretched it out vertically or flipped it over, same thing happens here. Multiplying that exponential by a number stretches it out if it's positive, well, stretches it out either way, but continues to stay above the x-axis if it's positive, or if it's negative, flips it over below the axis. So several examples we can do here, and I'm just going to do sketches. F of x equals 2 times 1/3 to the x. So there's two things going on here. One, this is my little a value here. It's smaller than 1. It's between 0 and 1. So that means this is going to tail to the right. Tail is the end where it goes to 0. The times 2 means it goes through at positive 2. So it's going to tail like that. If I have f of x equals negative 2 times 1/3 to the power of x. That's going to have the same effect, only it's going to also reflect it around the x-axis to give us that graph. F of x equals 2 times 3 to the x. So again, two things going on here. 3 is my value of little a. That means it's bigger than 1, which means it's going to tail to the left. The tail's over here. The 2 means I'm going to go through 2 instead of 1. Looks something like that. If I had f of x equals negative 2 times 3 to the x, we'll take that same graph and flip it over. Of course, there are other things we can do to move it around. So we have f of x equals 5 times 1/4 to the power of x minus 2 minus 3. Well, there's a lot going on here. First of all, this minus 3 here, it moves our horizontal asymptote from y equals 0, or the x-axis, down to y equals negative 3. Second thing that happens, right here, x minus 2, So instead of crossing wherever we would cross our y-intercept here, is not going to be the y-intercept, it's going to be over here at x equals 2. Basically, we've moved the y-axis over 2 spots. The 5, now it's positive, which means we are above the horizontal asymptote. It tells us instead of crossing 1 unit above the asymptote, which is where we normally cross, we're going to cross 5 units above the asymptote. And finally, the 1/4. Since that is between 0 and 1, it means we tail to this direction, giving us a curve something like that. So we really don't need to plot out points to graph these exponentials. Just like our other forms of equations we've looked at, there are clues within the equation that tell us how they get to be graphed. So in your notes, I'm going to have you try this. F of x equals -2 times 3 to the power of x plus 1 plus 3. Sketch out that graph. So the first thing that happens, of course, is it moves our axes. This plus 3 out here, what's going on here? There we go. That plus 3 moves our horizontal asymptote from the x-axis, or y equals 0, up here to y equals 3. Next, this x plus 1, remember, go the opposite direction, moves our effective y-axis over here 1 unit to x equals -1. So that basically serves as our origin right there. The -2 then says instead of being above the asymptote, we're below the asymptote. And instead of crossing 1 unit from the asymptote, we cross that vertical axis 2 units from the asymptote. So we can sketch in our graph like that. Any questions? Let's talk a little bit about solving an exponential. Many of our exponentials can be solved when they're in this form, 2 times x equals 32, by taking the other side of the equation and turning it into an exponent with the same base. What do I mean by that? Well, I mean this has a base of 2. Can I write 32 as an exponent with a base of 2? Yes, 2 to the power of 5 would be 32. So what that means is I can cancel out the base of 2 and just write the equation as x equals 5. If 2 to the power of x is equal to 2 to the power of 5, then if we have the same base, that means the exponents must be equal as well. X equals 5. We might have 7 times 3 to the x equals something like this, 63. Before we can work with that exponent, we have to isolate it. We have to get this part of the equation, the exponential, by itself. It's being multiplied by 7, so we're going to get rid of the 7 by dividing 7 by 7, giving us 3 to the power of x equals 9. Now that that exponent is by itself, or exponential is by itself, again, we'll do what we did over here. by expressing the other side of the equation also with a base of 3. Well, 9 is equal to 3 squared. So the exponents have to be equal. X equals 2. Well, there can be more to the exponents than that. We might have 5. Oh, let's see here. To the power of 2x minus 8 equals 15,625. The exponential is alone here. 5 to the power of 2x minus 8, that is the exponential. There's nothing multiplying it like there was here. So I'm good to start solving there. And what I'm going to do is I'm going to express 15,625 as an exponent with a base of 5. Now, I happen to know that 5 to the power of 6 is 15,625. I don't expect you to do that. So that's where guess and check comes in a little bit here. Now, next class, we'll look at how did you solve this brute force. What calculation can you get that'll reduce this for you? It'll tell you what to, 5 to what power will equal that. For now, it's just a matter of trial and error. We know that our base of our exponent is 5. If we did 5 to the power of 4, that's 625. Way too small. 5 to the power of 5 is 3,125. Again, too small. 5 to the power of 6, there it is. That's our 15,625. For right now, that's the only strategy we have for rewriting that as an exponent. Now that they're both bases of 5, we know the exponents have to be equal. So 2x minus 8 has to equal 6. Now we're going to go about solving the equations. We'll add 8. So 2x equals 14. And we'll divide by 2. To get x equals 7. So we might have something like this. This is about as ugly as it can get. 3 times 2 to the power of 3x minus 4 plus 7 equals 2,055. Actually, let me adjust that a little bit. Oh, come on now. So we get, it should be 6,151 is what it equals. So now let's go ahead and solve this. First, we have to get the exponential by itself. Remember, this part here is the exponential, the exponent, the base and its power. First thing I have to get rid of here, that exponential is multiplied by 3, and then 7 was added to it. We have to reverse that. We have to subtract the 7. We get 3 times 2 to the power of 3x minus 4 equals 6,144. Our next step is then to divide by the 3. Get rid of the 3. We divide out the 3. We've got 2 to the power of 3x minus 4 equals 2,048. Now that we have the exponent isolated all by itself, I need to figure out what 2 to what power is 2,048. We're going to represent the 2,048 as a power of 2. Well, that's 2 to the 11th power, correct? If we double check, if we guess and check. So that means the exponents have to be equal since we have the same base. 3x minus 4 equals 11, and we solve the equation from there. At this point, simple linear equation, we add 4, 3x equals 15, and we divide by 3. X equals 5. Now, they're not always quite that simple. Of course, right? We might have 4 the power of 3x minus 7 equals 32 to the power of 2x. We cannot express 32 as 4 to the power of something, but we can express both of them as 2 to the power of something. Now, let me take a look here. I'm going to step back for just a second. If I had, like, let's do 9 to the power of 2x plus 5. I can redo that as 3 squared to the power of 2x plus 5, where I just wrote the 9 as 3 squared. Well, what has to happen with these powers? I have 2 powers on that exponent. Remember, a power of a power, what do we do with the powers? Multiply them, yeah. X to the 5th to the power of 7, that's x to the power of 5 times 7, or x to the 35th. Same thing happens here. We're distributing the 2 through that power. 2 times 2x is 4x. 2 times 5 is 10. We multiplied the 2 powers. So 9 to the power of 2x plus 5 is equivalent to 3 to the power of 4x plus 10. So back to this example, we're going to do the same thing. Both the 4 and the 32 can be expressed as powers of 2. 4 can be written as 2 squared, the power of 3x minus 7. 32 can be written as 2 to the 5th to the power of 2x. Now again, the 4 you might see as 2 squared. The 32 you may have to take your calculator and try. 2 to the power of 4 is too small. 2 to the power of 5. There it is. That's the 32. Guessing and checking is appropriate here. Well, now I have to combine the powers. I'm going to multiply the 2 times the 3x minus 7. I have 2 to the power of 6x minus 14. On the other side, I have to combine the powers of 5 and 2x. 5 times 2x is 10x. Now they're equivalent exponentials, both with the power or the base of 2. So the powers have to be equal. 6x minus 14 has to equal 10x. And now it's a matter of solving the equation. There's nothing I can combine on each side. I have to make sure that the variable's on one side, so I'm going to subtract the 6x. So negative 14 equals 10 minus 6 is 4x. Then divide by 4. Negative 3.5 equals x. So x is negative 7 halves, or negative 3.5. I'm sure I've showed you before, but if it asks for this answer in fractional form, you would just take the negative 14 divided by 4 and treat it as a fraction. 14 over 4, both numbers can be reduced by 2, giving me 7 over 2, and it's still negative. I want you guys to try one in your notes that's a little bit longer like this. So the one we're going to try is this. 9 to the power of 5x minus 3 equals 81 to the power of 3x plus 17. Give that one a try. We'll go over it in a couple minutes. So for this problem, both 3 and 81, or both 9 and 81 can be expressed as powers of 3. 9 is 3 squared. That'll still be the power of 5x minus 3. And 81 is 3 to the 4th power. That'll still be the power of 3x plus 17. So I'm going to combine the powers, multiplying the 2 times 5x minus 3. So that's 3 to the power of 10x minus 6. Distribute the 2 just like I would in a polynomial. On the other side here, I'm going to multiply the 4 times the 3x plus 17. So that's 12x plus 68. So now again, I've written two exponentials where they have the same base. So that means the exponents must be equal. So the 3's are gone. We have 10x minus 6 equals 12x. I forgot my x there. Plus 68. Nothing to combine on each side, so I have to make sure the variable's on one side. I'll subtract 10x from each side. So negative 6 equals 2x plus 68. I'm going to subtract 68 from both sides. Negative 74 equals 2x. And finally, divide by 2. Negative 37 equals x. Any questions there? Okay. So I mentioned the term earlier, the terms growth and decay. Growth fits into these exponentials as something that's larger by a set amount or set percent each unit of time, or each period if you want to call it that. Decay means it gets smaller by a set percent for each unit of time or each period. To understand how this works, we need to talk a little bit about percents and talk about percent increase and decrease. I'm looking at a percent increase. Let's say I have an item that costs list price $80, but it's going to have plus tax of 5%. We could find that 5% tax, 80 times 0.05, which is going to give us $4. And to get the total, we could add them together. 80 plus 4 gives us $84 total. Or we could have looked at this and reasoned out that the whole amount, the $80, is 100%. And what we're adding to it is the 4%, the $4 is 5% tax. The final amount is going to be 105%. So if we had just taken the $80 and instead of multiplying by 0.05 to get the $4, if we multiplied by 1.05, which is 105% as a decimal, we would have had the $84 all in one step. Likewise, on a percent decrease, if you're hearing sirens in the background, I got the police science people in the next room and they're watching videos. No, they're not coming to take me away. You're not going to get that lucky today. So if we have an item that is priced at, let's go $30 with a 20% discount applied. Again, we could find the 20%. That'd be 30 times 0.2 or 0.20, which is a $6 discount. But then we would still have to do our $30 minus the $6 to get $24 that would be paid. Well, similar to what we saw in the increase, that $30, the starting amount is 100%. This time we're subtracting. For a discount, we're reducing the price by 20%. 100 minus 20 is 80%. So what we could have done here is just taken $30 times 0.80 for 80%. Would have given us that $24 net price in a single step. Well, that's what our growth and decay problems are based off of, is the percent increase and decrease like that. Let's say you currently earn $18.40 per hour with a built-in %4 raise each year. We want to find your wage in 7 years. Well, first of all, let's construct the exponential equation for this. F of t, the reason I'm using t instead of x is we're dealing with time. So it's traditional to use t as your variable instead of x. Is equal to our initial amount times 1, this is an increase, 1 plus our rate per period, rate of increase per period, times t, which is our number of periods. So A, our initial amount is $18.40. So we multiplied by 1 plus 4% is our rate. We write that as a rate, which is a decimal form of a percent, 0.04 to the power for 7 years would be t equals 7. I can actually punch that in the calculator exactly like that. 18.40 times parentheses 1 plus 0.04 close parentheses to the power of 7. Gives us $24.21. Now you'll notice that wasn't exactly $24.21. It was 24.231, but we had to round, or 213, I should say. We had to round it to those 2 decimal places because it is money. It's going to be cents. So in real life, this number might not be completely accurate because each year they're going to have to do that same rounding. Well, each year they're not going to necessarily go back to that initial number and calculate it out to get your wage for next year. They're going to take this year's wage and multiply by 1.04. Well, if it was rounded last year, that rounding can compound and it can throw you off in reality. But mathematically, $24.21 is where your wage should be at 7 years from now. Now, of course, that was an exponential growth problem because the number was getting larger. Let's say you're running a business and a value of one of your machines that you use decreases by 12% each year. It is currently worth $42,000. Find the value in 20 years. Now, being a decay problem, this is slightly different. Still a function of t, it's still our initial amount, equals our initial amount, times, instead of 1 plus r, though, it's a decrease, it's a decay. It's 1 minus r to the power of t. So we start out with our $42,000 times 1 minus 12% is 0.12 to the power of 20 years. Again, we can enter this in the calculator exactly like that. So 42,000 times parentheses 1 minus 0.12, close parentheses, to the power of 20. 3257.64. So the value should be $3,257.64 in 20 years. One common form of decay is radioactive decay. To understand radioactive decay, we got to discuss a concept called half-life. Half-life is the time required to decay by 50, to decrease the amount by 50%. So a 50% decrease. So our unit of time here is not going to be years or months, it's going to be half-lives. So if I know that the half-life of a given substance is 3 years, and the time that I'm letting it sit is 12 years, the number of half-lives is found by taking t divided by that half-life. 12 divided by 3, that's 4 half-lives. So that's my number of periods that would have to go over, is 4 periods, 4 half-lives. So we'll keep this example relatively simple. A substance with a half-life of 7 years has a mass of 800 grams. Find the mass after 20 years. Now I chose that 20 years on purpose. It's not an even number of half-lives. 21 years would have been exactly 3 half-lives. Doesn't matter. So our formula here is going to be f of t, or the amount as a factor of time, is equal to that initial amount times 1 minus 0.50, 1 minus 50%, to the power of t divided by, I'm just going to put in h for the number of, as the number of half-lives. Now, first thing you'll notice here, this is just 1 minus 50% is 50%, or 1/2. So this formula is often written as simply the amount times 1/2 to the power of t divided by the number of half-lives. So for this problem here, our initial amount is 800 grams times 1/2 to the power of 20 years divided by 7. Now again, we can enter it in a calculator just like that. So 800 times 0.5 to the power of, I'm going to put this power in parentheses, 20 divided by 7, close parentheses, 110.41. Of course, the 800 was in grams, so that is also in grams after 20 years. I'm going to ask you to calculate this. 800 times 2 to the power of negative 20 divided by 7. See what you come out with on your calculator. Oops. If you enter it correctly, you should find that you get the exact same value, 110.41. Why do those come out the same? Well, remember, a negative exponent is just a reciprocal. 2 to the power of negative 20 over 7 is just saying 1 over 2 to the power of negative 20 over 7. So these two expressions are equivalent. And that half-life equation is sometimes written instead of this form right here as a times 1/2 to the t over h. It is sometimes written as a times 2 to the power of negative t over h. Of course, our most common example of exponential growth is probably compound interest. Compound interest, there are two things we need to adjust. The rate. If I give you a rate of 8%, that is for a year. But our compounding periods usually are not annually. If it says compounded annually, you just use that amount. But if it's compounded quarterly, that means it's done 4 times a year. So express that as n equals 4, saying that it's 4 times a year. If it was monthly, n would equal 12. you would compound it 12 times a year. So the formula for compound interest is the future value, the value in the future, is equal to the present value times 1 plus. Now again, our rate of increase per period is not the annual rate, it's the adjusted annual rate. So it's the rate divided by the number of periods in a year. So R divided by N. And then our number of periods is to be, the number of years has to be adjusted by the number of periods in a year. If it was quarterly, that means there's 4 periods in a year. So the number of periods is N times T. So if you have $8,000 at 8% compounded quarterly for 3 years, that formula becomes the future value equals present value is 8,000 times, now in some of your calculators you do have to put that times in there, 1 plus, the rate is 0.08, 8%, quarterly is divided by 4, close the parentheses, it's to the power of 4 times 3. So 8, 1, 2, 3 times parentheses 1 plus 8%, 0.08 divided by 4, close parentheses, to the power of 4 times 3, I get 10,145.93. So $10,145.93. Dealing with exponentials, there's a number that needs to be mentioned. It's called the natural constant. The natural constant is a number just like pi. Pi is a set number. It's just a continuing decimal that never repeats in a predictable pattern. E is the natural constant. It's the same way. It's 2.7, blah, blah, blah. On your calculator, there's actually an E button. It's above the LN key. Usually it says E to the X. If I hit E to the X and just put in a power of 1, it gives me the value of E. 2.71828. Now it almost looks like on the computer screen that it does repeat 1828, 1828, but it doesn't. That's 1828, 1827 if I were to keep going to more digits. It does not ever repeat in a predictable pattern. But that natural constant, E, comes up in math over and over again if we're trying to describe things in nature. Growths of natural populations and ecosystems go off of that factor. Continuously compounded interest goes off of that factor. Anything that's happening continuously uses that letter E. What we've done up here, this was, it had that increase at the end of every period. Well, but it doesn't just wait to the end of the period and then have that increase. It's increasing at every moment in time. So let's say something that is constantly increasing at a rate of, let's do a population increasing at 6% per year. Now has a balance. Let's say there's 400 animals. So we're looking at a national forest where let's say we have 400 wolves living in that national forest right now. And their population appears to be increasing at 6% per year. Let's look at after 5 years. We could do that discrete increase where that that new amount is going to be the 400 times 1 plus 0.06, the 6% increase, to the power of 5. And that'll give us a good estimate. I'm going to leave the decimals on this, even though they're not real, they're kind of meaningless when we're talking about lives. Then we get 535.29. That's, between 535 and 536 wolves we'd expect to have in 5 years. But we could use that natural constant, telling us that the function of t is actually that initial amount times e to the power of that rate times time. So what would that mean here? That would mean the new amount is the 400 that we started with times e to the power of 0.06 times 5. So my calculator, 400 times second e to the power of, I'll put parentheses around 0.06 times 5. Close my parentheses. And I get 539.94. Notice it's slightly larger than that estimated value, and that accounts for the fact that the increased number, that 6%, doesn't just appear at the end of the year. They're coming along throughout the year. And because of that, some of them might already be contributing to the increasing population before the end of that year. So that natural constant E is a very powerful tool. We've got a couple minutes left, so I want to do a little foreshadowing into the opposite of an exponential, called a logarithm. Every operation we have in math comes with an inverse. If I take a number and I add 5, to go back to where I started, I'd subtract 5. The opposite would be subtracting 5. Multiplying by 3, the opposite would be dividing by 3. To the power of 2, the opposite would be a square root. Or the power of 5, the opposite would be a fifth root. The logarithm is the opposite, the inverse of an exponential. Remember I said the fourth root of 81 is really asking what number to the power of 4 equals 81? Well, if I have a log base 5 of 625, what that's really asking is 5 to what power equals 625? Notice this is an exponential. The base of the exponential is the 5. It becomes the base of the logarithm. The result of the logarithm is the power from the exponential. Now our calculator has only 2 bases that we'll look at next week. There's the standard log, log base 10, and the natural log, log base e, which is actually expressed as simply ln. We're going to explore those more next week. So there's a homework from last Wednesday that is due tonight. Well, actually, sorry, it's due tomorrow, due Tuesday. There is a new homework from today that'll be due Thursday. And then based off of the homework from Wednesday and today, there will be a quiz that'll be due Friday. And again, for those of you that have your tests back, Make sure that along with these assignments, you are working on test corrections. If you have any questions on the test that you're not sure how to redo, you can talk to classmates or you can talk to me. I'm more than happy to stick around after class and help answer any of those questions that you might have. So those are assignments that are due for Wednesday, or well, for this week, I should say. That's all we have. You guys have a great day. We'll see you on Wednesday. I will stick around here for a while in case any of you do have questions off that test that you would want me to go over for you today. Otherwise, I plan on sticking around each of the next several classes. Wednesday, I only have a few minutes, but next Monday, I'll plan on sticking around after class as well to answer any questions you might have on the test to do corrections on. You guys have a great day. Thanks.